So welcome everybody to this special seminar at IMK-TRO, which is the International Excellence talk by Professor Jason Furtado from University of Oklahoma. I welcome you. I'm glad to see at least some faces from the Institute here. I noticed that also some people are joining online. But I would also like to welcome Elena Pfeiffer and also Dr. Petra Roth from the International Affairs Business Unit of KIT, basically host this series of events. So the focus of the collaboration is very much on the subseasonal timescale of weather forecasting. That means everything between 2 weeks to 2 months is what is of interest to us. And I guess you can all imagine when looking at your phone and checking the weather forecast for the next 10 days, this already becomes difficult. And so even more difficult it becomes when we want to predict weather on a subseasonal time scale. So this is a real challenge. And we in the research would like to address this question and see this challenge, whether we can still improve on this time scale. Why are these subseasonal predictions important? You can think of the energy sector, for example. When we transition more to a renewable energy sector, we may need more storage capacities for renewable energy. So it's important to store that energy before, let's say, a period of low wind conditions. So we need to know already in advance, and this is on the subseasonal timescale, whether we need to store energy or whether we can just release it because we will have plenty of wind in the next weeks anyway. So this is one of the motivation. Then in Germany, we experienced quite some drought conditions in the recent years. There we think of water supply. What does it mean? Is there a drought coming up in the next month or so? And do we need to fill our reservoirs? Do we need to be save water already now before these drought conditions actually happen? So I think there are many applications where actually the subseasonal timescale is important, why we need a better forecast on that timescale. So what is the challenge of subseasonal forecast? Why is it so difficult? One thing is the chaotic nature of the atmosphere by itself. And I guess you all agree we can't do much about it. That's how the atmosphere is. But another challenge is that processes are not very presented necessarily in NWP models and numeric weather prediction models, which provide the forecast. So systematic biases therein take away some of the skill which we can expect from theory. And I think at KIT we have some history on subseasonal research, and this basically started with the Helmut's Young Investigator group of Christian Grams, who looked into processes in the mid-latitudes and identified the key weather systems which take away some of the forecast skill that can be expected on the subseasonal timescale. Where are now the chances for the subseasonal timescale? Is there any at all? And I would say yes, because we know that there are sometimes windows of opportunity, and these are driven by slower evolving modes in the Earth system. And that's actually also where our collaboration starts, but also the research in my group, which is currently funded by the ERC starting grant, where we actually want to exploit some of these slower evolving modes in the atmosphere, focusing very much on the tropical convection. As I said, with these sources, I think this is a direct link. And also this is one reason why Jason and I would like to collaborate. That Jason worked for quite some time on these slower evolving modes of the Earth system, which is, for example, on the ocean, on the stratosphere, so far up in the atmosphere. He also worked on sea ice and snow conditions and how they basically affect the longer timescales of the Earth system. And that's actually why we agreed to collaborate, now focusing very much on weather regimes, so slower modes of the atmospheric system in the mid-latitudes. We did that already for Europe, and Jason now does that more and more for the region of North America. And I think this is also linked then directly to the talk that we will hear today. So let me briefly recap the CV of Jason Furtado. Jason did his master's thesis or his master's degree in atmospheric science at Colorado State University in 2005, and then you continued as a PhD student at Georgia Institute of Technology, finishing the PhD degree there in 2010. And actually, I think what is a bit unusual is that Jason then decided to switch the sides and go more into the applied things, joining, I think, a company in the Boston area in Massachusetts. This is perhaps also interesting for the early career scientists, right? That we not necessarily need to stay in academia, but we can also divert from that and join the private sector for some time. And then after roughly 5 years, Jason applied for an assistant professorship, which he got at the University of Oklahoma, and by now in 2021 Jason was actually tenured and is now associate professor at the University of Oklahoma. So we are very happy to have you here, and with that I think I hand over to you, and I'm looking forward to your talk today.
Thank you for those introductions. It's very, very nice. Let me jump right into what we're going to talk about today. So what I want to talk to you today is some work that I've been doing over the last 3 or 4 years or so, looking at cold air outbreaks, particularly across the central United States, and really trying to understand both drivers of them and also how predictable are these on the subseasonal timescale. So Julian gave a great introduction about the subseasonal to seasonal timescale problem. I have it illustrated here in this diagram here. So on the y-axis is just an arbitrary measure of forecast scale going from excellent at the top to 0 at the bottom. The x-axis here is just showing time. The blue is for weather forecasts, orange subseasonal forecasts, and the purple for seasonal. Okay, so weather forecasts, these are 1 to 10 day type of forecasts, the ones you get on your app or you get from numerical weather predictions. And, you know, the day 0 forecast, typically excellent, scales down quickly after to 10 days to about 0 due to the chaotic nature of the atmosphere. If we jump over to the seasonal outlooks, these are boundary condition problems. I should have said weather forecasts are initial conditions, right? We set the model, we have the initial condition of the atmosphere and ocean, we let the model run and get a forecast. Seasonal outlooks are dependent on boundary conditions, so really more slowly evolving systems like the ocean and the land surface. Those we have some pretty good skill, decent skill going out months to even out to a year or so. But really where we're focusing in is this middle ground, sort of this gap area. This subseasonal to seasonal prediction. And why is this a challenge? Because it's actually a hybrid of both initial condition and boundary conditions. So in other words, we have to initialize our models with what's happening now, but then also rely on boundary conditions and other slowly evolving systems in the Earth climate system to inform us to get that added prediction out to, say, 8 weeks. And as you can see, pretty much not very good skill, poor to almost 0 as you get further out. Why is it so difficult? Because there's so many things going on that are affecting the subseasonal forecast. So this is actually a synthesis diagram from a subseasonal prediction task force that I was part of for NOAA back in 2016 to 2020. And this is sort of, again, sort of a conglomeration of all of the processes that we take into account when we're trying to make subseasonal forecasts. Now, admittedly, this is a pretty busy map, right? We've got everything going from storm tracks to atmospheric rivers to air-sea coupling to ENSO, tropical cyclones. And 2 things on here I'm going to particularly focus on for this talk. One is this stratospheric polar vortex, and the second will be this idea about blocking. And why am I interested in that? Because these tend to be A, very active during winter months, and B, cause some really extreme winter weather. And so getting ahead of those predictions, using those as predictors for the subseasonal space may help us to enhance our predictions out to that time point. Let's get everyone familiar with what I'm talking about when I mention these 2 things. So first, let's talk about the stratospheric polar vortex. What is it? This is a counterclockwise circulating air mass up in the stratosphere. So we're talking about 10 to 50 kilometers above the surface of the Earth. And it resides over the Arctic regions and forms during the winter. Why does it form during the winter? In the Arctic, it's cold and it's dark. So that's perfect conditions to have radiative cooling out. As the stratosphere cools radiatively, of course, we know that the relationship says that geopotential height fields must then start to lower, forming lower heights. And the geostrophic response is, of course, to produce strong counterclockwise circulation, westerly winds up there. The left shows what's called a stable polar vortex. This is when we have a perfect angular structure to it. It's spinning around. Typically, the westerly winds are going extremely fast up there. And what that does is, that's up in the stratosphere, but really the atmosphere is a fluid and it extends through the whole column here. And so what happens when this is spinning really tight up here, that also can translate down into the troposphere and start controlling the polar jet stream, the storm tracks across the middle latitudes as well. And when it's spinning tight, right, think about sort of a figure skater, as they bring their arms in and they spin faster, that's going to cause all of sort of that air to be pulled further northwards. And you can see that the polar jet stream pushes north. The polar jet stream is, of course, a division between cold air masses to the north, warmer air masses to the south. And so during a stable or strong polar vortex, the cold air gets contained in the Arctic, where it belongs. Storm tracks are further to the north, and you tend to get milder conditions across much of the mid-latitudes. Now, what happens when the polar vortex starts not being strong or starts to get disturbed? First, let's talk about how does it get disturbed? What disturbs it, right? It's up there at 10 to 50 kilometers above the surface. What can disturb it up there? The stratosphere is a stable layer. It's not like the troposphere that has all this chaos weather happening. Well, actually what happens is in the troposphere, we have these waves that form from our storms, and also because of land-sea contrasts and mountain ranges. Those waves don't just move horizontally, they can also move vertically as well. As these waves move up into the polar stratosphere, they encounter these strong westerly winds, and the waves can actually break, much like you might think about ocean waves breaking. When that happens, they deposit both heat and their momentum into the stratosphere. Now, if I add heat into a region that's cold, right, the temperature gradient or the temperature difference is going to start to weaken because I'm heating, right? So the north-south temperature difference now is not as strong anymore. It's not as cold where it was cold before. And we know what that means. That means also geostrophically, that means the westerly winds must also start to weaken as well because the temperature gradient is less. And as that happens more and more, the polar vortex gets weaker and sometimes can actually either be completely destroyed or actually split into pieces, as what's shown on the right-hand figure here. When that happens, remember I talked about as you have this column of air spinning, it'll spin the whole column off down to the troposphere. Well, now think about up here, if this starts getting kind of disrupted and wobbling in different ways, the tropospheric jet stream is going to respond the same way, and you'll get this very wavy jet stream that, as depicted here. Waves, of course, in the polar jet stream are going to cause cold air to start to move south into those trough regions or those southerly digs. And then on the ridge areas or the parts where the jet stream pushes further north on the wave, the warm air starts to move further to the north. And this is how you can start to build extreme type of weather conditions. It's also how, for example, you can produce atmospheric blocking episodes. Atmospheric blocking episodes, as you can see in the picture, is like that wavy jet stream that I showed in the previous, but instead what happens is this sort of gets locked in place. It's a traffic jam within the atmosphere. And so these pressure systems, say here we have a big high pressure system here over the central United States, and then areas of low pressure on either side. If these become quasi-stationary for days and days and days, of course you can imagine that the weather patterns are stuck just like you are in traffic. So under the high pressure, it'll be warm, it'll be clear, sunny, but under these trough areas, it'll be colder, rainier, etc., but continue for days and days and days. And if this gets stuck for a while, this is how we can form some pretty extreme types of weather. So where does this information, though, about the stratosphere come in and the blocking, but the stratosphere come in for subseasonal predictions? It turns out that the breaks that happen are when we have changes in both strong or weak polar vortex episodes. These tend to linger for days to weeks after the initial episode happens. So what I'm showing here is a real seminal plot from a paper in 2001 by Baldwin and Dunkerton. The shading here is defining vortex strength. And on this diagram, red is defining when the vortex is weak or when we have high heights. Remember, the vortex is an area of low height. So if we have high heights or higher than normal heights anomalies, that means the vortex is weak. The cool colors are showing, excuse me, that should be the other way, but the cool colors are showing negative height anomalies. So that's when the vortex is really weak. Excuse me, strong. So what happened, what they did in this paper was in the top, they took 18 events when the vortex was weak and did a composite. Pressure is on the y-axis, lag is on the x-axis. Day 0 is the day when the vortex was, say, the weakest on the top or the strongest on the bottom. And then the negative lags were days before that happened, and the positive days are days after that event happened. And I want you to notice two things from this diagram. Number one is in both diagrams, whatever's happening in the stratosphere doesn't just stay in the stratosphere. It propagates downward and eventually enters the troposphere. So you get same signed anomalies that enter into the troposphere as well. So when the vortex is weak or weakened, the days later, the tropospheric jet stream also weakens. Same is for the strong case. When the vortex is very strong, days later, the polar jet stream also intensifies and becomes much stronger. The second thing is, look how long that these anomalies last in the troposphere. Even when we go up into the stratosphere, by about, say, day 30, the anomaly is gone or weakened, but in the troposphere, they can last for almost 90 days after the initial event happened. This is where the predictability can come in for subseasonal timescales, using the stratospheric polar vortex as a potential predictor on those timescales. And of course, we care about it because if we have an inkling of what that polar jet stream is going to do, that can help us to understand perhaps extreme weather events. And so for the winter time in particular, we're talking about intense cyclones, we're talking about heavy snowfalls, we're talking about extreme cold, which will be the focus of this talk. And as Julian said, this has ramifications across multiple sectors, not just energy, agriculture, but also even human health as well. So in today's talk, what I want to take you through are sort of 3 small projects that I've been working on to sort of get an idea behind these cold air outbreaks and their subseasonal prediction, using the stratospheric polar vortex and blocking as sort of my anchors or predictors from that big diagram I showed you earlier. The first part, I'm going to show you how we've actually characterized and shown that different stratosphere-troposphere interactions are important to understand for long lead predictions of cold air outbreaks across the central United States. Once we do that, we're going to be taking a look at 2 case studies to get a better idea behind this. The first is going to be the epic 2021 cold air outbreak that occurred across North America. And we're going to actually do a prediction study with some subseasonal models to show which models actually predicted it and why we think that the model that did predict it well did so. The last part is actually going to be some new work that I've been working on with my PhD student, actually using a subseasonal model and running it and perturbing it ourselves to actually ask questions of, does the stratosphere matter? So what's cool about models, right, is I can turn off and turn on things and then run it and see what happens. And we'll see later that when I do an experiment of turning on and turning off the stratosphere, it matters for whether or not we can get a prediction of a cold air. That will be for a 2017 and 18 cold air outbreak that happened across the United States. So let's jump into the first part here, characterizing the drivers of central US cold air outbreaks. This is a work that was published in 2022 in the Journal of Climate. That's my PhD student there on the bottom there, Oliver Millen. So if we want to understand the drivers of cold air outbreaks, the first thing we have to understand is what kind of winter weather patterns do we even have across North America? And to characterize that, we actually go into these winter weather regimes. And Julian had mentioned some of this at the very beginning. We have here in Europe, there's an analog of about 7 or 8 of them that people use for their weather forecasts. For North America, we've done some similar type of work and defined them both for the year round, but specifically for this talk, I want to talk about winter weather regimes. So again, what is a winter weather regime? It's a recurrent large-scale flow pattern that happens in our atmosphere. And so here I'm characterizing the 5 most common winter type flow patterns that happen across North America. And they're here shown in the percentages are showing you the percent of time this was between 1950 and 2021, the percent of days, winter days, that featured that flow pattern. And the names, of course, I'll go through them here. So let's start at the bottom. Arctic low here, about 1 out of 4 days of the winter can be characterized by this. It's actually characterized by this sort of pattern of high, low, high across here. And you can imagine the storm track here going south of Alaska and then coming up and over into central North America. The second most recurrent is the West Coast Ridge, WCR, panel D. This is where we have very high heights, anomalously high heights along the west coast of the United States, and deep trough across, or lower heights across the eastern part of North America. Pacific trough is 1 out of 5 days, panel C. That's where we have intense Aleutian low. This is typical weather, flow pattern we see during El Nino years, where we have big low, but high pressure across much of North America. Arctic high can also be thought of in the European side, could be thought of as Greenland high or Greenland blocking, where we have intense high pressure over Greenland and lower heights across much of the southern area. So in other words, the storm track has shifted south across the central Atlantic and across much of North America. This tends to be a cold pattern. And then on the top right is our less frequent, but I will show very important Alaskan ridge pattern. This is where we have, instead of over Greenland, we have intense ridging or higher heights than normal that build across Alaska, and this allows deep troughing across much of central North America. So now that we have these characterizations, what we did was we went into the reanalysis record and we actually started looking for cold air outbreak events. And to define a cold air outbreak event, we chose within this boxed region across the central United States, that black box. By the way, here is, I don't know if you can see the cursor online, but here is Oklahoma, for those of you not familiar here. But really what we did was within this black box, we took the temperature to 2-meter temperature anomalies. And for 5 consecutive days, the 2-meter temperature anomalies within that box must be below the 10th percentile over the climatological period. We only chose days between December through February. And when we did that, we came up with 37 cold air outbreaks that occurred between 1950 and 2021 across that box. Great. So we have 37 samples. We can now start to look at, first, what's the flow pattern look like for these 37 events that occur and result in cold air outbreaks. And that's what's shown on the map on the left. This is 500 millibar composite map for those 37 events. The contours are the full field, so the actual 500 millibar heights. The shading are the departures from the average, but only for those that are 95% significant from a bootstrapping test. And when we look at this map, we can see some images of those weather regimes that I showed you earlier. First is this big ridge across the West Coast and especially across Alaska. That's our Alaskan ridge. And that actually accounted for about 19 of the 37 cases. So about half of the cases fell under that flow pattern. The other half fell over what we call the Arctic high. That's that Greenland block pattern here. That was about half of the cases as well. So now what we've done is we've narrowed down and said we have 3 of our regimes, 2 if we really kind of combine the West Coast and Alaskan ridge, 2 regimes that are very favorable to produce extreme cold air outbreaks across the central United States. But I talked about long lead predictions. So one of the things we're going to do is we want to look at the stratosphere. Does the stratosphere give us a hint about what may be driving these things to get to these predictions? So the right here shows composites, again, on those central US cold air outbreaks, lagged composites. So now, again, day 0 was the start of the event. The negative lags before, positive lags after. These are now the height, the same map that I showed earlier, but these are at 50 millibars. So we're getting now into the lower stratosphere. And what you can see is the contours are actually showing the polar vortex, that cyclonic circulation that I showed at the beginning, but it's not breaking apart. Remember I said usually when that breaks apart is when we start getting all this waviness and the cold air comes down and everything like that. We're not really seeing that here, right? Instead, if you want to imagine, these contours are kind of being stretched. It's not a perfect circle, they're kind of being stretched out. And that's especially apparent across North America, where you see these strong negative height anomalies, meaning that we're getting a shifting of that polar vortex towards the North American sector. So here's an immediate clue that we're kind of getting away from that classic paradigm of weak versus strong vortex for cold air outbreaks. We can see that nicely here in this plot. So this is similar to that dripping paint plot that I showed you from the Baldwin and Dunkerton paper. And let's focus on the right-hand panels first. So what we've done is we've done that compositing. On the top are composites, on the right are composites for geopotential height. So just like the maps that I showed you earlier, blue meaning strong vortex conditions and the red meaning the weak conditions. The top are composited for the Alaskan ridge cases. So these are the cold air outbreaks that fit into that Alaskan ridge flow pattern. And the bottom are the the cold air outbreaks that fit into the Arctic high pattern. They don't look the same, right? The bottom panel, panel D, looks like the dripping paint plot that I showed you earlier, where we had up to, I should have said the lags on the bottom. Day 0 is the start, negative is days before the event, positive are days after. The bottom right panel, panel D, looks like the Baldwin and Dunkerton plot. We had a weak vortex. They're up in this case, up to 1 hectopascal. And you can see that the anomalies descend with time. And by day 0, reach the surface. That's your classic sort of stratospheric breakdown, polar vortex breakdown influencing the surface. But what's really interesting is actually panel B. That's the Alaskan ridge cold air outbreaks events, right? Those are about 19 of them. You can see that we have blue. before. That means strong vortex conditions. So actually up to 3 weeks before a cold air outbreak that's under the Alaska Ridge pattern, the vortex is actually very strong. It's not weak at all. So this is already cluing us in that strong and weak doesn't necessarily tell us completely about cold air outbreaks potential across the central United States. And so this was a little puzzling. And so we were thinking, okay, well, why is it that half of our cases are preceded by strong vortex conditions and half by weak? Turns out that it has to do with how these waves interact between the troposphere and the stratosphere. So we're going to get a little bit into a little dynamics here, okay? Well, promise it won't be too much. So what do I have plotted here? So let's break it down. First, on all the panels, the y-axis is pressure in hectopascals, going from about 1 down to 1,000 hectopascals at the surface. The x-axis is now longitude, going from 60 degrees east out to 300 degrees east, so basically spanning from basically Eurasia all the way over into the Atlantic. The color contours are geopotential height anomalies. So blue versus red. Remember, red is like when the vortex gets weaker, and blue is when it gets stronger. And then there's arrows here, and that's actually wave activity fluxes. What's a wave activity flux? It just measures the actual way that the waves are moving in the atmosphere. So just follow the arrow, and it's showing you where the waves are going. And what we've done is we've done lag composites, the top for the cold air outbreaks from the Alaskan Ridge, the bottom for the Arctic high cold air outbreaks, lags going from days -11 all the way out to the start of the event. So let's take a look. Remember, our classic case is these waves go up and they break. Well, let's take a look first at our Alaskan Ridge cases. These were the weird ones where the strong vortex preceded. And what we're going to do is we're going to zoom in here a little bit and take a look. And what you can see is that we have upward waves coming out of the Siberian region. You can see those clearly here and here coming up. But look what's happening to the east of that over, say, Canada, North America, say, around that 260-degree mark. The waves are actually pointing down, which means the waves that went up are actually coming back downward. They're not breaking in the stratosphere. They're actually going up and coming back down over Canada. And you can see the response in the geopotential height field, where you get this massive ridge building that happens up to 3 days before the event due to this downward wave flux happening. So this is different. And actually what this is a phenomenon called stratospheric wave reflection. These are when waves go up, waves propagate through westerly winds. It hits a layer in the stratosphere where the winds are still westerly, but there's actually a wind shear there. So the westerlies actually start to increase and then decrease with height. So think about, if you look at a profile, a curved profile in the stratosphere, that's the perfect conditions to have a reflecting layer and cause the waves to then come back down. This is what's helping to generate those cold air outbreaks from the Alaska Ridge region. The strong vortex is setting up this layer that causes the waves to come up and come back down. The Arctic high cases are exactly what we expect. The waves go up over Siberia, and although you do see the waves coming down, you don't see the little yellow circles on there. I kind of forgot about that. The yellow circles are actually the significance markers, meaning that those negative or those downward waves are actually not statistically significant in our composite. Only the upward waves are. Part 1 summary here. North American weather regimes have distinct, unique relations to the stratospheric polar vortex, and it's different from this strong and weak case. More complex than that, right? Things are much more complicated. But the second thing is that extreme winter weather can happen under strong polar vortex conditions. And so it's not just enough to tell you, oh, the polar vortex is weak, so that must mean there's a cold air outbreak, or the polar vortex is strong, so there's not a chance of a cold air outbreak. We have to monitor both the shape, that stretching, and the way that these waves are moving up. So knowing all that, let's go ahead and take a look at 2 case studies. The first is the February 2021 cold air outbreak. This was an epic cold air outbreak across the central part of the United States. All-time record lows set in many of the cities. In Oklahoma City, it got down to -15 Fahrenheit, which I can't convert right now in my head to Celsius, but it is very cold. It's actually the coldest that had ever been in Oklahoma City since back in the late 19th century. According to our analysis of those 37 events, that 2021 event was the second most severe central US cold air outbreak, only beaten by the December 1983 event. Extreme damage to transit and utility and infrastructure across much of the plains. Unfortunately, about 280 people died from the cold, most of them in Texas, where they lost all electricity and heating for weeks. The official if you just count actual things that were damaged, it came out to be about $24 billion in US dollars damage. But when you start accounting for all the productivity losses and all the economic loss that happened because of this, and this is over a 2-week period, right? You're talking almost $200 billion in US dollars. That's more than some hurricanes like Hurricane Katrina caused across the US. So this was a major, major event that happened. How did this event evolve? So here what we have are actual evolution maps, 500 millibar geopotential height. The contours are the contours are the geopotential height anomalies. The shading are the 2-meter temperature anomalies. Here's the evolution of the event starting from the 1st of February out until the 18th, sort of the peak of that cold air outbreak. And what you'll see is there's 2 important features here that we're going to diagnose in this. First is this area of very strong high heights that develops across the Pacific, across the Bering Sea and East Siberian Sea area. This is one of those blocking ridges that I mentioned at the beginning, big high heights that develop there. That actually helps, if you look in the next panel, that actually helps to set up this trough that starts to load the cold air across southern Canada. And then the second feature is this large blocking high that forms over the Labrador Sea area between Canada and Greenland. And actually, if you look at the last panel, it actually moves westward or retrogrades back and sort of puts the squeeze play on that cold air mass. We've got highs over the Pacific. This thing kind of comes in, it sandwiches and pushes the cold air right straight down across central. How do we see these blocking highs form? Well, the way we can look at it is actually looking at potential vorticity fields. Here I'm showing the potential vorticity field on the 320 Kelvin isentropic surface here. The colors are the potential vorticity, and the thin contour is the 2 PVU, so that's essentially sort of a measure of like where the dynamic tropopause is. If you're not familiar with potential vorticity, the deep dark reds are supposed to be in the Arctic, and the lower heights or lower values are supposed to be more towards the tropics. And you can see in the top panel, you can see that there's this intrusion of lower potential vorticity that comes up into the East Siberian Sea at the beginning on the 2nd of February. And then that becomes sort of trapped up there, right in that black box. That's a wave break. Remember the ocean waves breaking? When the ocean waves break, it traps that low PV air there. That's a signature of a blocking high. Same thing is happening here, starting on the 9th of February. In the bottom panels, you can see this intrusion of low potential vorticity coming in. This is another wave break that's happening. And you can see that that air mass gets stuck in there, forming on the previous plot, forming that big high pressure or high area. So there's 2 wave breaks that set up these 2 blocking ridges that cause the squeeze play to push that cold air across the central US. So what we'd like to do now is we'd like to assess to see whether or not these key wave breaks are featured in the subseasonal models, because if they are, then maybe they had a chance of actually predicting these at longer ranges. So what we did was we looked at both real-time forecasts. So these are actual models that were run, initialized on the 28th of January, 2021. We looked at the ECMWF and also the NCEP subseasonal models. Today, I'm only going to show results from the ECMWF. The ECMWF has 51 ensemble members. We then went in and we did compositing of the potential vorticity fields, and we picked ensemble members which had the lowest potential vorticity across those 2 boxes, the Siberian Sea and the Labrador Sea, and the ones that had the highest potential vorticity. So the ones that have the lowest would be the ones that would be the best because they have the closest representation to what happened that we saw. The five that have the highest would be the worst because they didn't capture this wave break very well. And the target we're going to go is we have the initialization. Again, all the models started on January 28th, and we're going to look at their forecasts for the 2-meter temperature and 500 hectopascal geopotential height for the peak of that cold air outbreak, which was the 12th through the 18th. So we're talking about roughly a week 2.5 to week 3 forecast here. And here are the results for the ECMWF. The top row is the composite of all the best members, the ones that showed that wave break over the Siberian Sea, which I call wave breaking. The one over the Pacific. The bottom is the composite for the worst members. And what I want you to notice here are two things. Number one is that the best members, the worst members, the one on the lower, look what they're predicting for temperature, the shading across North America. They're all predicting red, which is actually warmer than normal, not colder than normal for that period. Now, the top members, they're not doing spectacular, right? We don't see this deep blue, but at least we're seeing that they're leaning towards colder than average conditions for that period. So there's some hint here that if they had gotten that Siberian Sea wave break, the models would have hedged a little bit more towards that colder wave break. But really the key comes for wave break number 2. This is the one over the Labrador Sea that then retrogrades and forces the cold air down. I think it's pretty clear, right? The top are the best, the bottom are the worst. The bottom, you would, in some ways, you might actually forecast even a heat wave across parts of the southeastern United States. Look at the deep, dark reds. We're talking about anomalies of over 8 Celsius predicted from. Whereas the colder than normal, the best ones you can see form this huge blocking high over Greenland, similar to what we saw, and the cold air coming across much of the central United States. So this is a key indicator, right? That this was a discriminating factor for which models produced better versus worse, was this actual wave. And so that's basically the summary, right? The main tropospheric features were the 2 blocks that happened, the East Siberian Sea and the East Labrador Sea, and the ensemble members, which got those wave breaks, especially wave break number 2, better captured that cold air outbreak. So the point of this is actually perhaps one benchmark or one area that we can start to look at our subseasonal models for extreme winter weather. How well are they handling wave breaks to form these blocking patterns that can form the extreme weather? The last case study here, sort of the last few minutes here, we're going to do a case study, but now we're going to do a little different. We're not going to look at the actual models. We're actually going to take one of those subseasonal prediction models and go in and play around with it and see if we can diagnose whether or not, in this case, the stratosphere was an important factor for the prediction. And this is work that's actually currently being in prep right now. So for this, we took the December 2017, January 2018, Central and Eastern US cold air outbreak. And the map on the left is sort of a composite of sort of the peak of that event, which was right around New Year's Day. And you can see this is a massive cold air outbreak that resulted across much of much of the lower 48 and parts of Eastern Canada. Temperature anomalies during that 5-day period, averaging about 10 degrees Celsius below normal. That's what's shown in the shading. The contours are the 500 millibar height anomalies, deep, deep troughs across much of the Eastern United States, very strong ridging across Eurasia, right, where there was actually a heat wave going on across much of Siberia during this time. Why? Because all the cold air exited and came and invaded the US, right? All the way across the Arctic. Now, I have this labeled. This actually in our database was actually one of those Alaskan Ridge cold air outbreaks. Remember, these are the ones that are kind of funny. They don't follow that strong vortex, weak vortex paradigm. They have this reflection thing going on, right? So was reflection happening during this event? Well, the answer is yes. So what we did was we can take an index of reflection, which sort of measures waves going up over Siberia, waves coming down over Canada. That's the black line. Whenever it's greater than 1, that's a highly reflective environment. You can see that during the x-axis is time that starts from the 22nd of November all the way out to the end of January. You can see that throughout much of December of 2017, the reflective index was 2 to 4 standard deviations. So there was plenty of reflective events happening during that time. The red and blue are just to confirm that. The red is showing the waves going up. So if it's positive, the waves going up over Siberia. The blue is the waves over Canada. So if it's negative, that means the waves are actually coming down over Canada. And you can see that indeed for much of December, that was happening. So now we have to go in and ask the question, did the stratosphere matter? It had this reflection going on, but did the atmosphere really care, or was something else driving this cold air break? Well, to do that, we're going to take a subseasonal model. In this case, it's the CESM2. And we're going to run it ourselves. It's a 21-member ensemble. Forecasts go out, you initialize it, we go out for 46 days later. Horizontal resolution of 1 degree, and 32 vertical levels going up to about 40 kilometers. And then, how are we going to test this? We're going to do nudging experiments. What do I mean by nudging? We're actually going to go into the model, and we're going to take the fields, certain fields, and we're going to start, the model is going to produce an answer, right? So I start the model, it runs for 6 hours, it's going to produce a new atmospheric state. I'm then going to go into that atmospheric state and I'm going to change it. And I'm going to change it. In this case, I'm only going to do it in the stratosphere. So only in areas above 100 hectopascals is where I'm doing fully going to change. Everything below that, really below 150, because we have to taper. Below 150, I don't change anything from the model. The model does what it's doing. But at each time step I go in and I change what the stratosphere looks like. And I'm going to do 3 different experiments. One is the free. Let the model do what it's going to do everywhere. I don't touch it. Just let the model run. 2 is what I call nudge ERA5. I'm going to take that stratospheric layer above 100 hectopascals and I'm going to nudge it to quote unquote the answer, what actually happened. So for example, if I start the model on December 1st and it runs, it's going to produce a stratospheric state 6 hours later, but I have what the answer was from ERA5. I'm going to nudge it towards that answer and then let the model run for the next 6 hours and produce a new answer and then keep nudging the stratosphere to push it to the right answer. Remember, only the stratosphere. The last one is nudge climate. In this case, what I'm going to do is I'm going to nudge the stratosphere, but I'm going to nudge it not to the actual answer, but what the climatology or what the stratosphere's climatology is for those states. So in other words, it doesn't know anything about what's supposed to happen. It just knows what typically happens in the stratosphere. So the idea here, right, if my hypothesis is correct, is that the nudge ERA5 should perform the best. I should get the best predictions from the nudge ERA5, right? Because that's the ones I'm telling you what the truth is in the stratosphere. If it doesn't come out that way, then that indicates that the stratosphere really wasn't a factor in making this prediction because the model still produced whatever it produced. Well, let's take a look. So we're going to take a look at 3 things. First is going to be 2-meter temperature anomalies across the Great Plains. And what I have here are probability distribution functions. So remember, I have a 21-member ensemble. I run the model 4 different times with different initializations. Initialization on the 27th of November. Remember, the peak was late December and early January. The 4th of December, the 11th of December, and the 18th of December. 2-meter temperature anomaly PDFs. The gray is the free run, so let the model do what it's going to do. The blue is when I nudge the stratosphere towards the right answer, or quote unquote right answer. The red is when I nudge it towards the climatology of the stratosphere only. And the target here, remember, is that last week in December and early January, those temperature anomalies across the central United States. Now, what I want you to see here is, let's first look at the gray, the free. It's at the beginning, at the early initializations, it actually follows pretty close to what the climate has, right? The first couple of panels there. Only later does it start to shift towards a colder or those negative anomalies later. The CLIMO, right, it's pretty broad, right? Especially on that 4th of December initialization. But what's key here is the blue, the nudge ERA5. Even at the early initializations, the nudge ERA5 PDF is pretty wide, right? Meaning there's a tail that actually suggests there are ensemble members that are predicting a potential of very cold conditions to happen. That's not apparent, particularly in the free run. And of course, everything, as you get closer to the event, everything starts to nudge better. Now, none of them do perfect, right? The black line is the actual anomaly that happened that week. None of them do perfect. I'm not saying that it is, right? And I'm not saying that the stratosphere is the only thing going on. But certainly if the stratosphere didn't matter, then I would not be seeing these nice sort of shifts that are happening in the blue PDF. Okay, well, that's just temperature. What about the actual flow pattern? So what we did was we went into each of those runs and we chose the three ensemble members that produced the coldest 2 meter temperature anomaly for that last week or that last period in December and early January. Free, nudge ERA5, and the nudge CLIMO. The bottom right is the answer. Okay, that's what actually happened during the week. And this is the 500 millibar height anomalies. And what you can see is, remember what we saw in our actual thing was this big ridge across the West Coast, deep trough here, big ridge across Eurasia. You can see that the free run shows that ridging is actually too far to the west. And so the trough is not quite as deep. The nudge CLIMO has the Alaskan ridge, but nothing in Eurasia happening. Only the nudge ERA5 shows this sort of West Coast and Eurasia thing. Remember, the model here is the model running on its own. This is not, the model at 500 millibars is not nudged towards ERA5, only stuff above 100 hectopascals. That's the difference between these. So here it indicates that telling this what the actual answer in the stratosphere was matters and helped to nudge the model towards the actual correct flow pattern. The bottom right here are just the spatial correlations for the North American sector of what the heights look like, and you can see that certainly the nudge ERA5 has the strongest correlation. Okay, this is the last slide here. Remember I said this stratospheric reflection mechanism was happening. It's an Alaskan Ridge cold air outbreak. So does the model care if stratospheric reflection was happening or not? Because that's sort of a central part of our hypothesis too. So again, we go into our model run here, the November 27th initializations. This is only from the nudge ERA5 one, so we're nudging it towards the correct answer. But now I stratify the ensemble members. I stratify on the top the ones that have very weak stratospheric reflection, and the bottom are the ones that have strong or prominent stratospheric reflection happening during December. Remember, these are initialized at the end of November. And what you can see, the difference here are number one, or the key difference here is all of the weak members on top look at the temperature anomalies across North America. Again, this is for those dates. Those are the target dates for those temperature anomalies. Most of the weak members all do not produce much cold air across much of the only the ones that had the strong or represented or had stratospheric reflection events within the runs during December actually produce a cold air. So the summary for this part is the nudging experiments do suggest the stratosphere did play a role in that event. It was a factor. Stratospheric reflection, in fact, was a key factor. And that's important because this was an Alaskan Ridge event. Now, caveats, it's one event. And are there other things going on? Sure. I'm not here to just tell you the stratosphere is the be-all, end-all. But really, I think this is pretty compelling evidence from just this modeling experiment that having a stratosphere in your subseasonal model that's correct makes a difference for these extreme winter weather events. So I'll just wrap up here with just some final thoughts. Number one, North American winter weather regimes and the wave mean flow interactions present these forecasts of opportunity that we need to monitor if we want to get better subseasonal predictions of extreme winter weather. Nudging experiments like the ones that I've shown here have the potential to advance our subseasonal prediction skill and really focus on that idea behind stratosphere, troposphere coupling and blocking episodes as being important. And the last bullet is just some ongoing work that's going on. So the stuff I'm doing here now under the International Excellence Fellowship is really focusing in on actually quantifying how well our numerical models predict those winter weather regimes at long leads for North America. We've also done a subseasonal prediction study of those reflection events. So overall, how do the models do? Spoiler alert, they do okay out to about week 2. After that, and then also there's ongoing work going on now through a Department of Energy grant where we're actually going into the model and doing some nudging experiments, but this time focusing on blocking episodes and getting the idea behind why these blocks form. With that, I'd like to thank you very much for having me and coming to the talk. Thank you.